Assalamualaikum and hello. I am Shahizan F1 with my fellow buddy Eman Shafiq, Fariza Hasmi, Ahmad Arizakwan, and Tuan Azam Aim Nafizi will present a few topics in FFT 1043 General Chemistry. Here I will share first about electromagnetic spectrum. Electromagnetic spectrum includes 6 spectrum which is gamma ray, X-rays, ultraviolet, infrared, microwave, and radio wave. For your information, gamma ray to radio wave, the wavelength become longer. We will start first with gamma ray. Gamma ray used in large industrial, such as sterilized medical equipment, sterilized foods, uses in tests in medicine, and a lot more. For the example, gamma ray also used in astronomy. These are produced by spectacular events in the universe such as star exploding, matter falling into black holes, and celestial object colliding. By collecting gamma rays, astronomers are able to see these violent events and can judge exactly how they shape the universe. Next is X-ray. As the wavelengths of the light decrease, they increase in energy. X-ray is a form of high-energy electromagnetic radiation that can pass through mass objects, including the body. X-ray travel through the body and strike an X-ray detector. X-ray used in a different way, such as medical imaging, security, radiation therapy, and a lot more. Here the example how X-ray is used. X-ray travel through the body and are absorbed in different amounts by different tissues depending on the radiological density of the tissues they pass through. Radiological density is determined by both density and the atomic number. For example, our bones contain calcium which has a higher atomic number than most other tissues. Because of this property, bones readily absorb X-rays and therefore produce high contrast on the X-ray detector. As a result, bony structure appear whiter than other tissues against the black background of a radiograph. Conversely, X-rays travel more easily to less radiologically dense tissues such as fats, muscle, and air-filled cavities such as the lungs. These structures are displayed in shades of gray on a radiograph. After X-rays, we will meet with ultraviolet radiation. Ultraviolet UV radiation is a form of non-ionizing radiation that is emitted by the sun and artificial source, such as tanning beds. Sunlight is the greatest source of UV radiation. Man-made ultraviolet sources include several types of UV lamps, arc welding, and mercury vapor lamps. Ultraviolet widely used in industrial processes and in medical and dental practice for a variety of purposes, such as killing bacteria, creating fluorescence effects, curing inks and resins, phototherapy, and stunning. Here I will show you how ultraviolet uses in phototherapy and stunning. Phototherapy uses two types of ultraviolet UV light to destroy cancer cells, ultraviolet A UVA or ultraviolet B UVB. Both types of UV light are administered using fluorescence lamps specially calibrated to maximize the effect of treatment while minimizing the risk of burns. The patient is first given drugs called surveillance. The combination of UVA and surveillance is called PUVA. The UVA light activates the drugs, destroying the cells the drugs came into contact with. UVB light is typically used to treat thinner skin lesions. Treatment with UVB light does not require additional drugs.
Okay, next after ultraviolet, we will move on to infrared. Infrared, sometimes called infrared light, is electromagnetic radiation with wavelength longer than those of visible lights. It is therefore invisible to human eye. Infrared is generally understood to encompass wavelength from around 1 mm to nominal rate edge of the visible spectrum, around 700 nanometers. Infrared use is for heat source, cosmetology, astronomy, massage therapy, infrared, and infrared photography. An example for astronomy is astronomers use optical devices like digital detectors, mirrors, and lens to analyze space object via infrared wave. We can obtain the image of this device from the infrared telescope. Next is microwave. Microwave are a form of electromagnetic radiation. That is, they are waves of electrical and magnetic energy moving together through space. Electromagnetic radiation spans a broad spectrum from very long radio wave to very short gamma rays. Microwave used by communication, navigation, radar, radio astronomy, and heating and power application. An example for microwave is microwave are electromagnetic wave having high frequency and small wavelength. So it is used in radar to determine the speed, distance, and motion of the subjects. The wavelength of the microwave is smaller, so they can be transmitted as a beam signal in the desired direction, and also microwave do not change their path. Hence, it's used in radar. Last but not least is radio wave. Radio wave wave from the portion of the electromagnetic spectrum at lower frequencies than microwave. The wavelength of radio wave range from thousands of meters to 30 cm. This corresponds from frequency as low as 3 Hz and as high as 1 GHz. Is it like 109 Hz? Radio wave communication signals travels through the air in a straight line, reflect off clouds or layers of the ionosphere, or relay by satellite in space. They are used in standard broadcast radio and television, shortwave radio navigation, and air traffic control, cellular telephone, and even remote control toys. And the radio used by standard broadcast radio and television, shortwave radio navigation, and air traffic control, cellular telephone, and remote control toy. An example for radio is radio control or remote control toys are self-powered and can be controlled from a distance using a remote that works with a radio wave. When we push the control button, the transmitter sends a specific number of electrical pulses corresponding to that action through the air. The transmitter has its own power source. Usually in the form of a 9-volt battery. Without the battery, the transmitter will not be able to send the radio wave to the receiver. That's it.
After that, we move to the second question. Subshell electrons are built through three principles, namely the Hahn rule, Pauli, and Aufbau principle. These three principles are used to determine the electron subshell. Hahn's rule is the principle used to fill electrons one by one into the orbit of each atom. It must be filled with one arrow first, then two can be filled. Hahn's rule principle is used if the subshell has more than one orbital. While the Aufbau principle is used, the principle that electrons are placed in the lowest energy first before they can be fed into the highest energy. An example, we must fill electron into 1s first, then 2s, then 2p, 3s, 3p, 3d, 4s, 4p, and so on. For the Pauli principle, electrons are filled into the subshell in the opposite direction of the arrow. An atom cannot have two electrons with the same quantum numbers.
How to write the electron configuration for an element in the periodic table? There are four types of subshell: S, P, D, and F. The S subshell has one orbital that can hold up to 2 electrons. The p subshell has 3 orbitals that can hold up to 6 electrons. The d subshell has 5 orbitals that can hold up to 10 electrons. And the f subshell has 7 orbitals that can hold up to 14 electrons. Example 1. S brought for beryllium element. To find the electron configuration of any element, we always start from hydrogen and make our way going from left to right to the element we are trying to find, which is in this case is beryllium. So, writing our electron configuration, since we start with the first row, hydrogen, is 1s1. We move on to the helium, which is 1s2. So we have 1s2. Next, we are on the second row, but still in s block. So 2s2, and we stop since we reach the element we wanted. This is the electron configuration of beryllium. Example 2. P block for sulfur element. We will find the electron configuration of sulfur by starting from hydrogen and making our way to sulfur. So 1s2 is the first part. Come back around onto the second row. 2s2 is the second part. Keep going straight across to the p block. 2p6 is next. Come back around onto the third row to 3s2. Keep going straight across to the p block in row 3, and we will come up until we get to sulfur. So 3p4. This is our full electron configuration for sulfur. Example 3. D block for iron element. We will find the electron configuration of iron by starting from hydrogen and making our way to iron. So 1s2, 2s2. Keep going straight across to 2p6, back around to 3s2, straight across to 3p6, come back around to the fourth row to 4s2. Now we are in the D block, and the coefficient or number in front is always 1 less than the row it is in. So instead of 4D, this is actually 3D. And we will come up until we get to iron. So 3D6. This is our electron configuration for iron. How to write the principal for electron shell using 3 basic rules: Pauli exclusion principle, Hund's rule, and Aufbau principle. Aufbau principle. Electrons are added to the lowest energy orbital until all the electrons of the atom are accounted for. In Germany, Aufbau means building up. This image represents that electron must be placed starting at the lowest energy level, which is 1s, then working its way up to the highest, which is 7p. Hund's rule. One electron must be in each orbital before pairing. For example, the bus seat analogy. A student must sit in each empty bus seat alone before sitting with another student. Based on the image, the first line is correct because all orbitals have an electron before being paired. The second line is incorrect because the electrons are paired before each orbital has an electron. Pauli exclusion principle. Each orbital can hold 2 electrons with opposite spin, meaning they face opposite direction. Spin can face up or down. Based on the image, the second line is correct because the electrons should are facing opposite direction in the same orbital. The first and third line is incorrect because the electrons should are both facing up and facing down.